Hello, my name is Virgil Goldberg, and this is my Physics 2212 Lab 3. So as a quick introduction, the purpose of this lab is to understand and visualize the magnetic field from a bar magnet. And then we're going to try and compare an experimental and simulation model to try and see the differences between real life and a simulation. So here's a quick preview of the result. We'll see that the result matched the overall trend of magnetic fields, so we'll see more in detail what magnetic fields should impact a different point at different places. We'll also see that the dipole moment and the field strength are found, but there's also significant error somewhere in the experiment, and we'll talk more about it later. So here are the key concepts. The main concept here is the Biot-Savart law. So this is used to calculate the magnetic field. So this is a change in magnetic field, and this is the base equation. Here we can see a bar magnet, so we can see that the magnetic field goes from north to south. From this equation, we can derive the magnetic field of a dipole in its axis and perpendicular to its axis, so those are these two numbers, and we can simplify the equation to the magnetic field being this. So this combines both of them. So the magnetic dipole moment can also be found this way, but we won't be using this necessarily in this experiment. But here is also another correlation where k is magnetic constants and n is, we'll see later, the gradient of, well, this equation, logarithmic equation that we'll talk more about later. So here's the experimental model. So the system is the phone here, the environment is the bar magnet here, and the earth that is, well, below here. And the assumption is that there's no other magnetic fields in the area. So the steps is first of calibrating the phone with and finding the chip of the magnetometer in the phone as an app. And then we'll have to find the distance on the axis, on the x-axis, where the magnetic field is 20, 70, 120, 170, and 220 microteslas. And then we'll have to find the distance for 100 microteslas, and then raise up the same value, and then measure the field there. So here are the results. So we can see here for the different values and the distances we find, and here are the averages, and this is for the last part of the off-axis. So when we use these values here, we get linear regression line. So we find that n is minus 3.028 that I previously talked about from this formula here, calculated as this, and k is the intercept, and ln k is the intercept, and hence k is this value here. So from these two equations, we can, which is this, we can solve for mu, the magnetic dipole, which is 1.675. So in the simulation model, we can see here that we plug in this dipole, and here we find this equation that I previously talked to that can find the magnetic field. Here we have the scaling as well as the distance that we've previously found here, about 0.16 meters. Here are all the observation points for the other points, and here are, so here is the distance once again that we've previously found, and here is where we calculate the magnetic field vector and also the magnitude of that magnetic field at that point. So here's a quick comparison. Here we can see the results of the simulation. So we can see that the field, these are the arrows of the field, and that they go, we'll say they go from north all the way to south. And we see that from the simulation, we get a magnetic field of 2.5 e to the minus 5, and from the experiment, we get 7 e to the minus 5. So this is quite a significant difference, but we still see that they both agree with the basic laws of magnetism, that a magnetic field is inversely related to the distance from the source, which we saw from the previous equations. For example, here we can see that as the distance increases, the magnetic field decreases. And so this has been proven here. So the possible source of error. So first, the magnetometer was very hard to keep constant and keep it in the north directions. Any small movements would completely, we'll say, move the values around. And the chip is not perfectly placed and measured. There's obviously a few movements, and because we're working with small distances, even 1 centimeter to the right or to the left makes a huge difference. There's also environmental impacts. Even though I tried to keep all of this far from any metals or any electronics, there's still quite a bit of a fluctuation, as I could see with, we'll say, the base value. And I've also probably made a few mismeasurements because I cannot measure, we'll say, smaller than the millimeter. So as an extension, what if you oriented your experiment to compensate if we hadn't compensated for the magnetic north, then all the results would be different because the Earth's magnetic field would not be only in one direction but also impact in the x direction, and we would have to recalculate everything to take into account the Earth field, or we'd have to just scrap it all and redo the experiment. And if we stuck two of them, then the two magnets back to back, then we'd have an overall trend would be the same, so it would just be a scalar multiple of the first magnet. It might not be exactly times 2 depending on the nature of the magnet, but yeah, it would be fairly similar. Thank you very much.